So in this video, we're going to talk about molecular compounds. So in grade 9, we introduce you the idea of molecular compounds, but we're going to re-emphasize and extend a little bit upon it this year as well. So I want to talk to you about the case where the third case where neither element wants to give up electrons, and so they end up sharing, okay? So when we have two atoms that are, instead of an electron being transferred, we're looking at sharing of electrons. What we've really formed there in that sharing action is what we call a covalent bond, okay? So let's look at that word covalent, okay? Co meaning together, like cooperate, okay? If you co-author something, you're authoring it with somebody else. So co means together. And valent means valence shell, right? So they are sharing their valence shell. And that's what happens in a covalent bond. Okay, so I'm going to use a simple example of hydrogen, okay, H2. And if I have H2, then that formula tells me that I have two hydrogen atoms together forming a molecule, right? So I have my one hydrogen atom with its one valence electron, and I have my other hydrogen with its own one valence electron. And at this point, neither of them are particularly happy or stable because remember, each atom wants its outer shell full. And for hydrogen, that one electron that it has is in its first shell, which means it would be happy with two electrons, right? So how is that going to work? Well, what happens is they end up sharing, okay? So in so doing, okay, so imagine that this right here, this hydrogen on the left, is this first blue circle on the left with its own nucleus, and there's its one electron, right? And then here's this second hydrogen over here with its own nucleus and its own electron. And what they do is they come together and they share this pair of electrons, okay? And so, well, why does that work? Well, it works because, you know, this first hydrogen's electron is attracted to the nucleus of the other hydrogen and vice versa, okay? And in so sharing, everybody's valence shell is full, and so that creates stability. Okay, so that is actually what we call a covalent bond, is that sharing of electrons. And you'll notice when those atoms come together, that creates what you'll learn in grade 11 to be an electron cloud. Okay, let's talk a little bit more about this so that you get exposed to another example. I want to use the example of chlorine in this case, okay? So what we just saw was a molecule. So anytime you have two or more atoms joined together, then that forms a molecule. And so molecules are joined by those covalent bonds. So in this case, the Cl2 molecule, you know, find your Cl, find chlorine on the periodic table. And you will note, and it's a good idea for you to find this yourself, don't just take my word for it, okay? But chlorine has 7 valence electrons. So notice here on the left, I've written one of the chlorines in this Cl2 molecule, and on the right is a different one. Now, I've used different colors to denote where the specific electrons on the two different chlorine atoms. Okay, and so, you know, neither of these guys really wants to donate an electron to the other guy completely, right? You know, like in an ionic compound, neither of these guys wants to lose electrons, okay? Even though each of them needs one, neither of them wants to give up any electrons. So that is the case where we're going to see these guys want to share, okay? And so what happens is they come together and they do exactly that, they share. And so I see on the left here that the chlorine on the left, we can count that one electron here in with the valence shell of this chlorine. And then I can count the blue electron as part of this chlorine's valence. Okay, and so everybody is stable, right? So what they have here is they have a shared pair. Okay, so they have a shared pair. Let me go back there. Okay, so whenever you have a shared pair of electrons, that is what we call a covalent bond. Okay, so let's take a deeper look at this. And so I want to kind of, you know, compare that to what we've seen with ionic compounds to show how they're different. Okay, remember, covalent bonds, sharing of electrons. Ionic compounds, transfer of electrons. Okay, so ionic compounds we actually don't call molecules. It would be a mistake to call NaCl a molecule because there's no actual bonds forming because there's no sharing of electrons. Okay, all we have is we have one atom giving an electron away, transferring it so that we form ions, but there's no shared pair. They're just attracted to each other based on those opposite electrochemical charges. Okay, so no sharing. Molecular compounds form covalent bonds, and we can call that a bond, and we can call the compound that results a molecule. Okay, so let's keep talking. So usually we say that molecular compounds we can identify as molecular because of the types of elements that they're made up of. Usually molecular compounds are made up of two or more nonmetals. Okay, now let's look at the periodic table to try and make sense of this. Okay, now ionic compounds, we know we've got our metals that have extra electrons they want to get rid of, and nonmetals that want to gain electrons. But in the case of nonmetals, so I've gotten rid of all the metals here, if we have two or more nonmetals coming together, then we're dealing with all of these elements where neither of the two or more in the pair really want to get rid of any electrons. So the only way that they can kind of come together to form any sort of stable particle is if they share electrons. Okay, so how are you going to identify from a formula if a compound is molecular or ionic? Okay, if it is ionic, you will see it's composed of a metal and a nonmetal. If it is molecular, then you will see that it is composed of two or more nonmetals together. Okay, all right, so more about that. Because the formula of a molecular compound is like representing the actual number of atoms that are present in that molecule, we never reduce our molecular compounds to lowest terms. Now, let me give you an example to illustrate that. Okay, so I have P4O10 and P2O5. Now, in both of these cases, you can see that the ratio 4 to 10 is the same as the ratio 2 to 5, right? But the difference here is that I have phosphorus and oxygen in this molecule, both of which are nonmetals. That is telling me that this is a molecule and that the number of atoms that are represented here describe the exact number of atoms that are bonded together. And that these are completely different molecules with different chemical and physical properties. Okay, so for example, here is P4O10 with exactly 4 phosphoruses and exactly 10 oxygens bonded in a very specific way. Whereas in P2O5, I have exactly 2 phosphoruses and exactly 5 oxygens bonded in very different ways. Okay, so what is the message here? Okay, even though these have the same ratio of atoms, they are different molecules, and we're not going to reduce molecular compounds formulas to lowest terms in the same way that we do with ionic compounds. Okay, last piece, and this is going to be important more so when we get to chemical reactions in the latter half of this unit. Okay, I want to talk to you about what a diatomic molecule is. So you didn't know about this, but I sort of alluded to the idea of diatomic molecules in our review of grade 9 chemistry, but I want to talk about it specifically here. Now, the prefix di typically means 2. So a diatomic molecule is a molecule composed of 2 identical atoms. Okay, and there are some molecules, there are some molecules that exist, okay, some atoms that really don't exist as individual atoms in the world by themselves. They simply aren't stable, so they just don't do that. And so they form little pairs with another atom of their same kind, okay? They're like twins. So the 7 diatomic molecules that you need to know are these ones. Okay, hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. Okay, so these are all diatomic. You're never going to see nitrogen as an atom existing in the world on its own. You're never going to see oxygen as an atom existing on its own. These are always going to be paired up. They're always going to be twinned. Okay, those are diatomic molecules. So one way that students will remember them is to remember this mnemonic. And I call it Hofbrinkel. Okay, so Hofbrinkel, here we have all the letters of the elements that are diatomic. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Right? So another way to remember is where they're located on the periodic table. Okay, so let me see if I can draw this. Nope, not gonna happen. But hydrogen is all here by itself, so that's, you know, just remember H2. But, you know, all the others form kind of like a 7 here. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine. And these guys too, but we're not going to worry about them so much. Okay, so right here, NOF, and then Cl, Br, and then I. All of those are going to be our diatomic elements along with hydrogen. Or you can just remember Hofbrinkel. Okay, all right, so predicting the formula with, you know, molecular compounds is really hard. We can't use the crossover rule because the crossover rule works with ions, right? Positive and negative ions. But, you know, we're not forming ions in molecular compounds. We're just sharing electrons. So we can draw what are called electron dot diagrams to show how these atoms are arranged. And that becomes a bigger piece of what we do in grade 11 chemistry as well. So let's start with water. You know, we know water has the formula H2O, okay? And so let's look at the elements, you know, the atoms that are in H2O. H2O means I've got 2 hydrogens and 1 oxygen. Okay, so my oxygen has 6 valence electrons, and I get that from my periodic table, okay? And each hydrogen has 1 valence electron. Okay, so my oxygen's not super happy. Right? And my hydrogen is not happy because neither of these have a full valence shell. And so what happens instead is they share. Okay? And here's a covalent bond right here. And here is a different covalent bond formed with water. Now, another way sometimes we show that that pair is shared is we replace the 2 electrons with a stick. And that's sort of more of a grade 11 way to show it. So, you know, this red and blue electron that are paired together here as being shared, we might replace with a stick. Okay, so here we have 2 sticks because we have 2 shared pairs. Okay, so I want you to try this next one, nitrogen trichloride. Try to do that and see how that works for you, and we'll take it up together in a minute. Okay, so I've switched to my Jamboard here, and I want to talk about this. So you should know that, you know, one way to differentiate between the electrons coming from one atom versus another would be to show dots of different colors. But if you don't have 2 different colors, this is often how we can show that. So let's say we were showing nitrogen with its 5 valence electrons. We might show the nitrogen like this, but we might show the chlorine instead as having a different symbol. So like, for instance, often you'll see X's, right? So chlorine has 7 valence electrons, so we might show it as having X's instead. Okay, so that's just a quick solution that you can use to differentiate if all you have is one single color. Now, I have different colors, so I'm going to show this in different colors. So I'm just going to get rid of all this and kind of backtrack. Oopsies. Here we go. So nitrogen trichloride. All right, so your ability to do this is, again, going to be a function of whether or not you know the trend on the periodic table and how many valence electrons that each element has. And so nitrogen over here is in the 5th row, again, ignoring the transition metals. And so it's going to have 5 valence electrons. So I'm just going to show that in here. And I also have chlorine, which has 7 valence electrons. And actually what I'm going to do here is I'm actually just going to reposition one of these electrons just so that we can more easily kind of deal with the chlorines. Okay, I know that each chlorine, I'm going to do chlorine in a different color here. Each chlorine is over here, and so it has, counting over across the groups, 7 valence electrons. And so my chlorine here would have 1, 2, 3, 4, 5, 6, 7. Okay, and so chlorine is going to share one of the pairs, one electron pair with nitrogen. So I'm just, for right now, just going to kind of show that they're sharing. And I'm going to show you how we need to move forward from that and depict this. But for now, I'm just going to show that now this chlorine is happy because it is now sharing an electron with nitrogen. Okay, but nitrogen's not happy yet. It's going to need to find 2 other chlorines to share with. That's why it's Cl3. And so, you know, showing that on this other side here, I'm going to try to squeeze in this chlorine. So Cl, right, with its electron, it's got 7 of them, same as before. And it's going to share that pair, right? Okay, now finally, I've got one last nitrogen electron, and I've got one more chlorine to deal with. Right, and so this last chlorine is also going to have 7 valence electrons. And it's going to share a pair. Right? So what I want to do from here is I need to show what that will look like in a more sort of appropriate representation. And so I have 2 ways to go about that. Okay, I can either show it as, like in this depiction, with my nitrogen in the middle and its own 5 electrons, and then each chlorine around it. So here's the shared pair with the chlorine that's on the right. Here's the shared pair, that's this right here, with the pair on the left. And then here is that last shared pair with the chlorine that I'm showing sort of below. And if I want to show how everybody's happy, I can say, well, here is my nitrogen, and around it, it has its own 8 electrons, right? If I want to show this chlorine right here has its own 8 electrons, as does this one right here. And as does this one right there, because they're all kind of like sharing with each other. So if you were able to get that, fantastic. If not, and my going through it was not helpful to you, make sure you reach out and we can kind of keep working at it together. Okay, I've got one last example for you on this, and that is carbon dioxide, which has the chemical formula CO2. And I want you to try that on your own, and then pause the video and give it a whirl when you are ready. Okay, so let's take a look at this. So, you know, carbon dioxide, I'm sure you have probably heard about. We talked about it in our bio unit, but, you know, what does it look like chemically? So I would start by finding my 2 elements. So I'm going to start with carbon. And I'm just going to kind of place it right here. And I know it has 1, 2, 3, 4 valence electrons. And so in the formula, it tells me that I have 2 oxygens. So I'm going to be looking to find 2 oxygens. Here's oxygen, and it's in the 6th row over, again, ignoring those transition metals. And so I'm going to write each oxygen out with its 6 valence electrons. So 1, 2, 3, 4, 5, 6. And I'm going to do the same thing over here with the other oxygen. 1, 2, 3, 4, 5, 6. So hopefully you kind of started there. So when I look at this diagram, I can see that, my carbon has 4 electrons, which means it needs 4 more to be happy. I can also see that oxygen needs 2 more electrons to be happy. And so I have 2 oxygens, each needing 2 electrons, and carbon having 4 to be able to donate. So that actually works out pretty darn well. So instead of them sharing 1 pair, they're going to need to share 2 pairs. Okay, so this oxygen over here is going to share this one and this one. And my second oxygen is going to share this one and this one. Okay, and so what that creates is what we call double bonds. So instead of having a single covalent bond, we create a double covalent bond. Okay, and so what that looks like when we kind of put that all together is, let me switch colors here, is I would have my carbon with, these 2 electrons right here, just like right here, sharing with these guys' electrons right here. So let me write that out. So oxygen. And it's got the 2 there in that those shared pairs. Okay, but then it's got, these other electrons here that I still have to put in. Okay, they're still there. 1, 2, 3, 4. Okay, and so I'm going to do the exact same thing on the other side. Okay, so I've got carbon's 2 other electrons. And then I've got my oxygen with its 2 electrons in the 2 shared pairs, and then the other electron pairs around it. And don't worry too much about where you're putting those other electron pairs. Now, here's 1 electron pair. That's 1 covalent bond. This is another covalent bond. Same here and same here. So a way that I would depict this in a sort of more mature or sort of advanced way would be to replace those covalent bonds with sticks. So I'd have my carbon and each oxygen, and the oxygen would still have its valence electrons that are like sort of not in the bonds. But then I would replace each shared pair, like this shared pair would become a stick. This other shared pair would become a different stick, and so on and so forth. Okay? And that is how I would draw a molecule of carbon dioxide. All right, so that is all we have for today for molecular compounds. So if you have any difficulty with anything that I've talked about today, make sure that you check in with me. And also please note that what you should be working on next is the inquiry assignment on properties of ionic and molecular compounds. And complete that as soon as you can. That will go in as part of your inquiry mark for this unit. If you're struggling with any aspect of it, make sure you contact me. We can get together on Zoom and work it all out.